John Santiago, founder and CEO of Freedom University. What you'll be seeing are a series of educational videos that should supplement your textbook, classroom, or homeschool learning developed at Freedom University. These and other short videos on various technical topics are currently available online. In these series, we'll be talking about the Laplace transform. This is a very useful concept if you want to understand how linear systems work. That is, what will the output look like for a given input and for a given system description. When you convert a waveform or function described in the time domain involving integrals, derivatives, or differential equations, these operations are relatively difficult. However, you can simplify the analysis when you convert the time description of the system and inputs to a function described in the Laplace or frequency domain. The analysis is a lot easier since in the Laplace domain it involves only algebraic manipulations to find the output. So if you have any questions on any of these videos or in locating them, please contact me at the following email at john@e-liteworks.com or pronounce as john@eliteworks.com. Or you could visit my social and multimedia website at freedomuniversity.ning.com. There at freedomuniversity.ning.com, I will keep you posted on the latest multimedia ebooks that we will be producing. I and other entrepreneurial professors will be producing more multimedia educational products to increase your higher education, including topics in engineering, investing, and marketing. I hope you enjoy the following video clips about summarizing the Laplace Transform Table. Previous videos have led to the following video summary. Thank you for your time and happy learning. Now let's look at a summary of the Laplace Transform Table. Here we're going to take a look at all the functions that we reviewed so far, the basic Laplace transform pairs, where you have three columns. The first is the signal or function, the middle column is f of t, and the last column is f of s. So let's look at the impulse function, symbolized by this delta, and we have its corresponding Fourier transform pair to equal 1. And in this case, the key point you want to remember in this case is that anything that's in one domain that's very thin is very wide in the frequency domain. So in this case, this delta function only occurs at t equals 0, and it becomes very wide in the frequency domain or Laplace domain. Now the step only occurs for t greater than or equal to 0 in this case. So we have a unit amplitude 1, and its corresponding Laplace transform that we saw is 1 over s. Now the ramp can't be generated from the step function, as we know that when you integrate a step, you get a ramp. But we know that the symbol for an integral is 1 over s, and the Laplace transform for a step is 1 over s also, so that leaves that the Laplace transform of a ramp is 1 over s squared. Now we come to the exponential, e to the minus alpha t. Here we have the unit step multiplied right here just to show that this exponential exists for t greater than or equal to 0. And we saw that the Laplace transform is 1 over s plus alpha. And for the case when alpha is equal to 0, that leads to a step, which makes sense because when you substitute alpha equals 0 in the time domain, you basically have a step function. Now you have a damp ramp, which is a combination of the exponential and a ramp. But we saw in the modulating property, okay, that whenever there's an exponential in the time domain, it corresponds to a s plus alpha in the frequency domain. In other words, you replace the s with s plus alpha. So here for the ramp, we have a 1 over s squared, but it has a damping exponential. We replace it with s plus alpha squared. Okay, and when you multiply this, it's s squared plus 2 alpha squared plus alpha squared when you complete the square right there, or do the complete multiplication. So you have a middle term there. And in this case, we'll take a look at that with the sign, because the sign has s squared plus alpha squared, but when you calculate the roots of the denominator, it's purely imaginary. So that beta is just the frequency of a sinusoidal function, in this case beta. So if it's purely imaginary, that corresponds to a sinusoidal function frequency. Likewise for cosine, we just have a s in the numerator and the same denominator as the sine, s squared plus beta squared. Okay. Now we have a damped sine, but we saw that the modulating property says in the time domain, replace everywhere there's a s, we replace it with s plus alpha. So here in the sine it's beta over s squared plus beta squared, so we replace the s squared with s plus alpha squared. And that's all there is to it. And then finally, for the cosine, we have one at the numerator. So we place the numerator s with s plus alpha and the denominator s squared with also with s plus alpha squared, and we get this function. Notice when you multiply or the denominator here, we're going to have a s term that have a coefficient of 2 alpha s, and that corresponds to a damping term, which corresponds to alpha. So whenever you see evaluate the roots in the denominator and it consists of a real and imaginary component, we know that the real part corresponds to the damping exponential and the imaginary part corresponds to the sinusoidal function with a radian frequency of beta. Okay, so hopefully that gives you insight to complex numbers for the Laplace transform when you look at the roots of the denominator of the Laplace transform, because this is going to be a very powerful technique to give you insight to the behavior of systems when you start looking at the transfer function associated with a system and evaluating the roots of in the denominator of the transfer function corresponds to the pole or cutoff frequencies associated with that system. And that's it with the basic Laplace transform pairs.